Hello, and welcome to this video on convergence of a series. We have the summation from 1 to infinity of 1 over the cubic root of n, and we want to find out if this series converges or not. So notice that the first thing we see is that the nth term is 1 over the cubic root of n. That term, that nth term, becomes really small as n goes arbitrarily large. So the limit of an as n goes to infinity is 0. Here we have the limit of 1 over the cubic root of n. Because n is huge and it gets larger and larger, the cubic root of n is huge, and then 1 divided by something enormous is just getting closer and closer to 0. So in the limit, we have 0. This tells us that there is hope that this series converges. At least we can't discard that the series converges at this point. So now let's move on to the next part. Now we're going to match the nth term of the series with a function at n. So here notice that an is the same as substituting n into f equals 1 over cubic root of x. And this function f is continuous. It is decreasing and positive as long as we keep to numbers between 1 and infinity. If we look at the graph of a function, then we see that this function is going down. It looks like a hyperbola kind of thing. And from 1 to infinity, the function is decreasing. That's the region where it looks like a hyperbola kind of thing, because it isn't decreasing before. But from 1 to infinity, the function is decreasing, positive and continuous. And then what we can say, thanks to the integral test, is that convergence of our series is equivalent to having convergence of an integral. If this series converges if and only if an integral converges, and it's the integral from 1 to infinity of the function f of x. So to study convergence of our series, it's enough to study convergence of an indefinite integral, sorry, it's an improper integral because we have infinity as one of the bounds. So let's look at the integral from 1 to infinity of f of x, and let's see if that integral converges or not. If the integral converges, then we have convergence of our series. If the integral diverges, then we have divergence of our series. We will see that the integral diverges. So now the integral from 1 to infinity of f of x dx is the integral from 1 to infinity of 1 over the cubic root of x dx. And by definition, we have that this is the limit as b goes to infinity of the integral from 1 to b of, and let's rewrite that root as a power. We have 1 over x to the 1/3 dx. So we're working with the limit of the integral from 1 to b of x to the negative 1/3 dx as b goes to infinity. And to work with the definite integral, we use the fundamental theorem of calculus. We find an antiderivative of x to the negative 1/3. That's x to the negative 1/3 plus 1 over negative 1/3 plus 1. We forget about the constant, and we want to evaluate this antiderivative at two values. One of them is b, the other one is 1. We find the limit as b goes to infinity of, and then minus 1/3 plus 1 is 2/3. We can check that. The 2/3 So we're making b huge and evaluating, or better, evaluating first and then making b huge. The evaluation is b to the 2/3 over 2/3, and then minus 1 to the 2/3 over 2/3. 2/3. There we go. And when b is huge, b to the 2/3 is huge. So its limit is going to give us infinity. Because b is on top and we have a positive power on b, then b to the 2/3, b to that power, is really huge as b grows arbitrarily large. So the integral diverges. Since the integral diverges, does not converge, doesn't give us a fixed number, it gives us infinity, we can say that our series diverges by the integral test. Okay. So we can summarize what we did as follows. We have a series to work with. The first thing we do is we check that the nth term goes to 0. If the nth term doesn't go to 0, then we can already say that the series doesn't converge by the nth term test. If the nth term goes to 0, then we move on and we try to see what happens with the series. In this particular case, we can say that the nth term of the series can be matched with f of n, where f is 1 over the cubic root of x. And this f happens to be continuous, decreasing, and positive from 1 to infinity. Then we can use the test, the integral test, that tells us that having convergence of our series is the same as having convergence of an integral, the integral from 1 to infinity of f of x. So then we check the integral and we see, because the integral is computable, then we find that approaching convergence from convergence of the integral is easier. The integral of f of x dx from 1 to infinity is infinity. Because that integral diverges, then we can say that our series diverges. Okay, so that's it for this example. Thank you so much for watching. If you have questions, please write comments and I will be happy to help you. Bye-bye.